Right. Okay. So today we're going to be talking about connectedness. Um, so connectedness has to do with it's actually a lot simpler of a property than compactness. So we'll first define something called a separation. A separation of X is a pair U and V of disjoint. By the way, disjoint just means that their intersection is empty. Disjoint non-empty, so both U and V are not equal to the empty set. Non-empty open sets with X equal to U union V. Okay. That is a separation of X. We define our topological space X to be connected if there does not exist a separation of X. So right off the bat, one of the things to keep in mind when doing proofs about connectedness is that the definition of connectedness implicitly has this sort of negative feel to it, right? You're defining something by saying that, like, our property is that saying that something doesn't exist. So a lot of the times when we're dealing with proofs using connectedness, we want to use the approach of contradiction, right? If we want to prove that something is connected, we would assume that it is disconnected or not connected, and so we would assume that there is a separation, and then we would use that to arrive at a contradiction. That is the most common way to deal with connected sets. So the first thing, this is very important. If Y is a subset of X and Y is connected, and C and D are a separation of X, then Y is contained in C or Y is contained in D. Excuse me. So, why is this true? Because essentially, if C and D separate X, then Y intersects C and Y intersect D. These are both, how should I say this? These are both open. Well, C and D are open. So these are open in the subspace topology of Y, right? And of course they're disjoint because C and D are disjoint. So so these are open and disjoint, and of course if we were to union them together, then we would get y intersect C union D, but C union D is x, so y intersect x is y. Y intersect C union y intersect D equals y intersect C union D, y intersect x, which is y. But y is connected, so this can't be a separation, but we know these are disjoint and open sets, so this must mean that therefore y intersect C or y intersect D is empty. And for whichever is empty, y is contained in the other one, right? So if y intersect C is empty, then y is contained in D. If y intersect D is empty, then y is contained in C. So here this makes use of, these are open in the subspace topology on Y. The next thing is if we have a family of connected subspaces of X, and the intersection of this family, so let's say the index set here is A, the intersection of this family is not empty, so this family shares a common point, then the union of this family is connected. And for a proof of this, essentially, you would go by contradiction. You would assume that this is disconnected, so you would say, okay, if I have a separation of this union, then each y sub alpha is either contained in C or D, but each y sub alpha contains some common point P, meaning that each y sub alpha every y sub alpha is either contained in C or D, right? Because P is either in C or D. It can't be in both because C and D are disjoint. So that leads to a contradiction, because if all of the y sub alpha are contained, say, in C, then the union of the y sub alphas would be completely contained in C, and its intersection with D would be empty, which is a contradiction, because we assume that it is not empty. The next thing, which is a useful property to show, is if C and D are open and disjoint, then the closure of C and D are disjoint, right? And you would prove this by contradiction. So say P is in C intersect D. If P, so then P is in D, so P is not in C, but P is in C closure, right? So P is contained in C boundary. Now, D is open, so any neighborhood, remember a neighborhood is just an open set of P is contained, or not, sorry, so there is a neighborhood of P contained in D, but by definition of the boundary of C, this neighborhood must intersect C, since P is in C boundary. This is a contradiction, since C and D are disjoint, right? Because if the neighborhood is contained in D, but it contains a point in C, then that means that point in C is contained in D, which is a contradiction, right? You can't have a point being in both C and D. Once you have proved that, you can prove that if A, so let A be connected, if a set B is sandwiched in between A and A closure, then B is connected. And again, you would just prove this by contradiction. So proof by contradiction. So let B be separated by C and D, then A is contained in C, or A is contained in D. So then either, right, this is sort of an exclusive or, then either A is contained in C or A is contained in D, because A is connected, right? Right, we already proved this. So we can say, and the fancy term here is say without loss of generality, A is contained in C. What this means is that the proof here on out is not dependent on whether A is contained in C or A is contained in D. It's going to use the same logical steps, and we might as well label C based on the fact that A is contained in C. We know it's going to be contained in one of these, and we can always just rename them so that A is contained in C. Then a closure is contained in C closure, right? Because remember, the closure preserves set inclusion. But then B is contained in C closure. Sorry, I'm blinking here. So C union D is contained in C closure. And since C is contained in C closure, this must mean that D is contained in C closure, which is a contradiction, right? Because C and D are open and disjoint, so D and C closure are also disjoint. The next thing is, just like with compactness, if we have a continuous function f and A is a connected subset of X, then the image of A is connected. And once again, you would prove this by contradiction. You would say, suppose we have a separation of f of A, then we can then we can derive a contradiction from that. And one last thing is a somewhat, I'm not sure how useful it is, although it is something rather interesting. As an alternate definition for connectedness, X is connected if and only if the empty set and X are the only subsets of X which are both open and closed. The reason being is that if B is open and closed, then X equal to B union B complement is a separation, right? Because B is open and B complement is open, and these are disjoint. So you know, we have a contradiction that way. Of course, this only proves one direction. You have to also show the other direction. But yeah, that is it for this lecture. Do you have any questions?
I'm clear, sorry.
All right, then that's it.